So, welcome to my presentation about precise garbage collection in D. My name is Rainer Schütze. Most of you might know me from my work on Visual D, Visual Studio package for supporting the D programming language, including project management, language services, and debugging support. When I'm not working on D, I'm working for Steinberg Media Technologies. It's a company in the computer music industry, most known for their digital audio workstations, Cubase and Nuendo. I'm working on musical instruments there, and we do this in C++, so that's my background. So in my talk, I will give a short introduction to garbage collection. I'm afraid it will repeat a bit of what Leandro has shown you yesterday, but maybe it will be with another twist to it, because I'm referring to precise collection, whereas Leandro has taken the pause time mostly into consideration. Show the current GC implementation shortly, and then present the precise garbage collection implementation that I have done, and we'll discuss further improvements that might be necessary to improve it further. So what is garbage collection? It's known to be the automatic memory management releasing unreferenced memory. So what it actually does is it scans memory from some roots. This is the global data segment or the stack or registers, and looks for references to allocations that are in the heap, and transitively follows these references to all live objects. All objects that are allocated but are not found, referenced, are then discarded as garbage. So what are the benefits of this approach is mainly that you don't have to care for ownership management anymore, as in C++, and avoids quite a number of bugs that happen quite often, like dereferencing an already freed pointer and double freeing memory and so on. Resulting of this automatic ownership management is an inherent memory safety with multithreading. And this also enables other kind of algorithms that can be more performant than when you have to do it manually and have to allocate and free very consistently. And especially in the D language, it allows an easy use of array slices and delegates with stack closures, where in theory you could manage that memory manually by explicitly freeing the underlying arrays or the stack closures, but you really don't want to do that manually. On the minus side, there's some drawbacks that you usually have with automatic garbage collection. That is delayed memory reclamation. That means that you don't do it, that you don't scan the heap too often, because it does need CPU power, and so you just do it once in a while, and as long as you don't do it, memory allocations pile up, but there might be still some unused memory still in the heap. Usually also garbage collection introduces pause times during the collection. That's what Leandro was talking about. And depending on the type of garbage collection, you might also have some read or write barriers. That is, if you change a pointer, you have to somehow add additional code to just change, to just writing the memory location, but also have to log it somehow or have to change reference counts or something like that. And also, depending on the garbage collector, it might be vulnerable to false pointers. I will come especially to this property here with the precise garbage collection. Whether a program is faster with or without garbage collection depends very much on how it's implemented, what the allocation rates are, and so on. So there are basically 4 different garbage collector types. One is mark and sweep. That means while the world is stopped, that is, everything, all threads are paused, the heap objects are traced, as described before, and it's usually non-moving. That is, every heap, every allocation block stays where it is, but that causes fragmentation problems, very much like you are used to in C++ as well, where you don't move heap objects around. To fight this fragmentation problem, there are approaches like mark compact. They use the same marking phase for finding live objects, but then move objects in place so that the live objects form a contiguous space in the heap, and so there's no more fragmentation. And one additional big advantage is that the free space is also a large contiguous space, and allocation is very effective and very performant. Copying is a variant of mark compact in that it also moves the heap objects around, but it doesn't do it in place, but into another space that was previously unused, and this simplifies the tracing a little, so it's called scanning sometimes. But both approaches have the disadvantage that you have to move data, and that is also costly sometimes. The fourth kind of basic garbage collector is a reference counting collector. That means in each object there's a counter how many references it has, and this is decremented whenever a new reference is assigned, incremented whenever it's assigned, and decremented if it's cleared. This adds a read and write barrier usually, and it's also non-moving, and it's also difficult to free memory if there are cycles in references. Usually to resolve those cycles, you have to go back to one of the other approaches to free that memory that is used by these objects. You can combine those different algorithms with you can combine them so you collect partially with this algorithm and another part with another, and that goes to generational garbage collection, and you can also make them concurrent. But usually those approaches need some kind of read or write barrier. So a conservative GC has no type information about the memory that it has allocated. So that's like also in C++, you might know the Böhm GC that works like this. And the assumptions that such a garbage collector uses is that memory references must be aligned to a machine word. So a pointer cannot be aligned to some odd address, and that pointers are usually at the beginning of the allocation or inside the allocation. It's possible that pointers are derived. That's a more general case of an interior pointer, so that, for example, it points to before the actual allocation memory, but that would not be detected. This also poses some restrictions on what a compiler can generate as code if it's optimizing, say, array operation on multiple arrays that work in step. It might choose to just have one pointer and work with the differences of the pointers to address those arrays, and that might cause problems if this is the only reference to the memory that is accessed there. Because there's no type information for memory, the garbage collector cannot distinguish between values in memory that are actual pointers or values that are just random numbers. So these are called false pointers if they actually point to or have a value which address is identical to some object that has been allocated on the heap. And because it cannot distinguish between these, if a value is actually a pointer or not, it must not modify it. So a conservative garbage collector can never move objects around. So this garbage collector is actually a conservative mark and sweep. So it's, well, pretty basic conceptually, but because missing type information doesn't allow almost anything else. It stopped the world. All threads are paused during tracing, and it uses a segregated fits allocator. That means it puts allocations of a given size into bins. That's in this size, in this case, into powers of 2, and maintains free lists of allocation spaces where these where free objects can be allocated from. For allocations larger than 2 kilobyte, there's a large object space where allocations are in page granularity. Sorry. So assuming a similar distribution over object sizes in the lifetime of a program, the segregated fits allocator with the free lists is kind of safe from fragmentation, though it cannot really return memory to the system because normally there's still some objects still allocated in a page that has been partitioned into those bins. In case of the decompiler, we have one optimization in that the compiler generates information about in classes and structs whether this object has any references inside or not. So we can distinguish objects that have no references, so and they don't have to be scanned from objects that have to be scanned. So let's see it at work. And here's one example of what I experienced with Visual D, and that's why I worked on this precise collection. Sorry, Jonathan, again, standard daytime. Here we are just simulating editing a file, and each edit, after a short pause, forces a repass of the file to display parse errors. And this file has more than 34,000 lines of code, and more interesting is the size of the file, which is read on block as about 1.5 megabyte. It creates 350,000 ASCII nodes, and each node is slightly more than 64 bytes in size. That aligns to the next multiple of 2, next power of 2, and that is 128 bytes per node, and this yields about 50 megabyte of information in memory for one pass. So when I repeatedly run this loop, this parsing, you see here how the memory usage actually is. The red line is the memory of the pools that are allocated by the GC, and the blue line is the actually used memory. And what you see is, and the black lines here show when one pass has been finished. And what you see here is that memory increases continuously until it runs out of memory. And for 60 seconds, after 60 seconds, we only have 18 passes because most of the time is eaten by the garbage collection. So just to have a ref.
Yeah, is it 32 bits?
That's 32 bits, yeah. Just to have a reference, here in this example here, I'm just freeing the AST manually, though this might be unsafe if any reference anywhere in the program would have been stored somewhere. And this shows what to expect if the garbage collector would work perfectly, and that is about 2 times the size of the trees is to be expected, because before the pass is complete, there's always the old version of the file still in memory. So we have twice the memory of one AST memory. So why does it go so badly? One reason is that we have very huge, that the nodes have pointers to their children, and the children have pointers to their parent. So in effect, all those 50 megabytes are just as one block. If you reference one of them, you keep everything in memory. So what I implemented then is that I disconnected the AST. I just removed all the references to parents and children, and that yielded a better result. I have scaled it here to 200 megabyte, but it still shows that during execution of those parsers, memory still continues to rise, but at some time it gets slower. And after a minute, for example, it's 227 megabytes in contrast to 150 for the manually freed memory. So here I have zoomed the first 10 seconds of this phase here. And what you see here is actually the blue bars show the time where the collection runs, and the red bars show the time where the program actually runs, while the brightness of the red changes with every pass. So you can see how it advances. So what we see here is also that the allocation strategy of the GC can be improved, because in the beginning it is using a lot of time for just collecting garbage, although it cannot really free a lot. And what you also see here is that garbage collection time is about linear dependent on the number of live objects. That is, in this case, the number of the size of the used memory. If in these cases the number of live objects is reduced because it can free one full ast, and then it drops slightly.
So Sean and I discussed a number of times about this. How do you think we can improve the strategy there? Because there's this pattern in which the GC kicks in, does a pass, figures out it can't free a lot. But then there's a change of phase there, if you wish. At the time you reach the plateau, actually it's a good thing that it kicks in. So what thoughts do you have around improving the behavior?
Well, I guess the initial memory usage, or the strategy there, is very much to minimize actually used memory. It doesn't fit with memory allocating that much. It starts at 4 megabytes for a pool, and then very slowly increments only for each new pool. So this application is rather allocation heavy, and so it kicks in very often, and also so I would say we should simply start with larger pools at the beginning, and so it doesn't kick in that often at the start. And at the same time, we have if a collection fails, you see here that it's usually or the collection doesn't fail, but it returns very little memory. It still continues. It allocates a new pool, but maybe the threshold is also a bit low, so it could allocate more, especially in systems that have a lot of memory, as is normally now. So, what are these false pointers? Or what happens if we hit such a false pointer? So, if, for example, 4 megabyte allocation is hit by some random value on a 32-bit system with a probability of 0.1%, and if you add that probability for 1,000 values, you get a probability of 63% to pin this memory with 1,000 random values. So with a bit more, you're almost likely to pin this memory block
although that's a good statistic, I think it's misleading, because I don't know the exact figures offhand, but integers in software aren't random. They tend to cluster in values pretty near 0. So if you're if your collector pool,
random values. I don't say any value.
Okay.
Here so I say what I think are good random values for good candidates for false pointers.
Okay, I just want to say that it's not as bad as that
Yeah,
statistic.
sure. It's not 1,000 values. Usually they are very small, yes, but.
Actually, some kinds of values have a higher probability of being considered false pointers than others. For example, ASCII, just text, it usually points where there generally Windows allocates heap, where it allocates the address range for heap as well as I remember some discussions about some big problems with floats. So although integers, I mean, like numbers like we encounter in real life don't trigger false pointers as much, there are lots of other kinds of data types that do.
Yeah, floats is also good.
Also, there's a lot of high entropy data occurring in many programs, such as compressed data, JPEG, movie data, and
Well,
any
these
compressed
data is usually just plain data and is marked as no scan, so it's not often a problem. But especially if data lies in the data segment, there's no possibility to add this information. This part doesn't need to be scanned. So these make very good false pointers. That is GUIDs. I don't know if you know, that's a Windows term for global unique identifiers. This is a 16-byte, more or less random value to identify interfaces. Hash values are also meant to be distributed equally across the number space. Encoding tables, like you find in standard uni tab, and strings in the data segment are also not so bad candidates.
Sorry, to answer your previous question, maybe we could use something like branch prediction, but for garbage collection to predict for a given which are the likely program counters IDs that give rise to successful garbage collection. So at least in the previous case, that would work very well. So kind of something similar to branch prediction, but here for garbage collection prediction.
Well, it has to be perfectly correct. You cannot give probability, oh, it's by 90%, it's not good enough.
It doesn't have to be perfect. It just triggers. It tells you when's the likely candidate to trigger garbage collection.
It's the previous issue. The whole when do you trigger a collection?
Ah, okay.
The previous graph.
Yeah, also, okay.
Right.
That you can, okay. Yeah. So for 64-bit, it doesn't look that bad because you have to hit a lot smaller smaller part of the address space to generate a false pointer. But it's not 2 to the power of 64 as a probability for a single hit. But because user space is limited on all operating systems to 47-bit, that does not include the system bit for the highest bit, on Linux and OS X, and 43 bits on Windows. And depending on where the addresses for usual heap allocations start, you might find some patterns that also produce false pointers. For example, struct like this has some alignment space between the pointer or the reference here and the 32-bit value, and it's filled with 0, so it's more likely to produce a false pointer to Windows, under Windows. For OS X, you would have to not 0, but a small number to be more likely to be a false pointer. Under Linux, heap address starts at 7FFF, something from top down, and that's less likely to produce a false pointer because it would need to have especially those values here, and more unlikely. So, to precise garbage collection to the cure, we need type information for the memory to distinguish pointer fields from non-pointer fields. And which memory areas do we have? We have the heap, as discussed, the global data in the binary image, thread local storage, stack registers, and manual managed memory. So I will first concern myself with the precise garbage collection for the heap memory. This is based on the Google Summer of Code project by anti-Villeturjainen, and which was mentored by David Simcha. It generates compile time a bitmap of pointer fields at compile time for each struct or class, and the GC malloc operation copies this into some extra memory alongside the pool. So looks more or less like this, that you have a struct here, and this is translated to a bit field for each for each pointer, that this object or this next pointer is one in the bitmap, and if an object of this type is allocated, you will have this bitmap is placed into the info bitmap alongside the heap. So if the heap is marked during the collection phase, only those bits that are set in the info bitmap are actually scanned for pointers to other objects. And this especially also allows in placing new types into partial memory areas. That is, if we would like, for example, make a standard in place on the starter part here, we could, in general, change these bits only here to reflect that there are references now inside this area. So in contrast, there's also another standard approach that stores a pointer into for each allocation block. Depending on the size of the allocation block, this needs more or less memory, but the threshold is rather large here. For small allocations, it will need more memory than the bitmap version. Also, you might, if you store it at the beginning of the allocation block, you might run into problems with alignments that you usually want to have 16-byte alignment for each new allocation, as it is presented to the caller of the malloc function. And at the end of the allocation block, it's more work to find actually the info pointer, and it currently would interfere with the array handling, which also stores information at the end of the allocation, though that would be feasible. And if you put it alongside and similar to the info array, that would need even more memory if you want to have it pre-allocated, because you don't know the size of the object, so you would have to allocate one per granule that is 16 bytes. That is the minimum size of an allocation. And you lose the possibility to place such type info into the pointer bitmap. So how is it generated at compile time? We have the type info here that has a property that has been added about a year ago, and this virtual function RTinfo is supposed to return any information that's unknown to the compiler what it is. But for class and struct type infos, there is a member inside this class, and the compiler fills this member of the class when it generates the class type info with the result of the invocation of the template RTinfo on the type. So we just forward the template invocation to our GC templates, and then we set up the bitmap here. Here we enter CTFE from template information. We enter CTFE to generate that bitmap as an immutable data structure. And well, I don't want to go into every detail, just wanted to show that it's not really a lot of code. It's here it allocates the static array and calls this function to set the bitmaps. For classes, it has to call the composite class because it needs to assume that it's not a reference to a class, but the class instance itself. This theme will, we will see this again also, and for all other types, it just forwards to another function that sets the bits of the bitmap. For composites or for aggregates, like a class or a struct, it checks the base class and invokes it recursively and then runs the bitmap set function for each subtype. Just here, one note about this tuple of. This is an array of symbols to the t-point tuple of is an array of symbols to the members of that class or struct. So we can get the offset of that symbol inside the struct and then place or set the bitmap accordingly. This is happening in this function. Don't want to go into every detail, but it just goes through all the possible types with a static if and then calls this set bit function to change the field in the static array to set the appropriate bit for the pointer info. So the runtime interface has a very simple extension. All those allocating functions for the GC, they get an additional type info information, parameter, and this will be used then to extract the runtime type info. I have added this function here, GC, in place to make it possible to actually change or to put a specific type into that memory area. This is necessary, for example, for those for the array handling, where the interpretation or the alignment of data changes depending on the size, and for also associative arrays where there's where the type is more or less not fully given, but in partial. You have the key and the value as two different type infos, so you have to place those explicitly into one block of data. And the actual malloc function does call a set pointer bitmap function to actually move that RTinfo into the bitmap array. So what we see here is the actual improvements that we have from this implementation. The green line is the previous result without with a conventional GC, with a fully, and the red line is the pool size of that implementation. A bit disappointing, I would say, because it's not as good as the manually. Could need some improvement. And the main problem is that a lot of false pointers are in the data segment. We haven't handled these. So what we need to do is that for all, or that's what I have implemented, is that for all global data variables containing references, the compiler generates pairs of address and type info, so these can be passed to the garbage collector and then scanned instead of just assuming it's a range of untyped data. This is currently hard-coded into the compiler. It would be nice if we could support it somehow as another template that would be able to describe how to deal with those data fields in the global section. But this is currently not easily possible because we cannot specify to put it in a special data section. So the runtime the linker could combine all these and put them into a separate area that we can then pass to the garbage collector. And data relocations for thread local storage variables are currently not possible. We could generate code for that, but still would need a hack to go through all the threads then. So, yeah. Still, there's a slight problem with the type info of class references, because if you actually emplace an object of type class into the data segment, you cannot distinguish it from a reference because we have no way to describe that as a type from the type info side. So if we do this, we get this result. Again, the conservative garbage collector, and now we have almost the same flat line as a manual collection. It's only 1 megabyte more of pool memory used here. So it's almost precise. We have covered the heap. We have the global data in the binary image and the thread local storage data covered. And the stack is kind of a problem because it cannot really, it's hard to describe pointers on the stack at the moment. But we have stack stomping, that is a rather new switch, which overrides the stack memory used by a function if it exits. And so these pointers from this function cannot leak into other functions that do not use this space in the code path that is actually executed, but in some other code path, and that could leak some unused pointers could leak in other functions on the stack. Registers is even harder to describe by type info. So, but these are only very few values, so we might be able to live with this. Manual memory could be treated similar to the global data image, but I haven't implemented that. But it's more or less the same problem. So the restrictions of that implementation is that there are no type informations currently for delegate closures. This means that if a delegate has to take a closure, it just doesn't allocate memory without this type info parameters. And so the garbage collector has assumed that pointers are contained conservatively. If this would exist, it would also help debugging, because that information could also be used by the debugger to display closure variables. It's currently also not possible to move objects because this one bit cannot describe whether it's maybe a false pointer or definitely maybe a pointer or definitely a pointer. So, for example, in the case of a union, where it's just the binary OR of the bitmaps of the members of the union, or a void array, which can have anything. So this could be added with another bit in this information, and then some objects could be moved. But I'm not sure that is desirable. And you would have to adjust all the references then. So when using emplace in this implementation, you will have to need extra care, because if you have references in this data area, you must have this type info set before. So there might be a race condition with the garbage collector and the information that is placed into the pointer bit map, because the garbage collector might miss this info before it's actually before the reference is invalid. So, and this the current restriction is also that this implementation of the RTinfo is currently only for Win32. So, what would be nice to have to improve the garbage collector is some way to generate this RTinfo for the data segment. And one way I would propose is to have a pragma data seg that allows to specify where data is put into a binary of this information for the linker. So this is a concept used widely on all platforms and is used by quite a bit of possible execution types like DLLs or drivers or something like that. Regarding the RTinfo, this is currently only just a void pointer. But there are also already other people using this for other kind of information to generate at compile time. So it might need to be extended somehow. And one way would be to maybe just make the type info a fully library-defined template, so that the library would define which kind of additional information would be generated into this struct or class. There was also a pull request, I'm not sure if it was accepted already, to generate immutable class instances into the data segment. That would help here quite a bit. So type descriptions for closures are needed to be more precise. And regarding the ambiguity, whether the type info for a class is its reference, so only the pointer actually, or is for the full object in memory, might well, makes it indeterministic which one is actually news, and you have to make some assumptions about it. So maybe we need some type info reference or something like that to actually describe what is in this memory area. One big problem is still the stop the world issue. Leandro has proposed some rather impressive stuff, but still it might be interesting to look into more complex garbage collectors like generational or concurrent garbage collection. But these need a write barrier for pointers to record changes, so the garbage collector can keep some consistent view of the current state of memory. And to implement that, that would be necessary to have some kind of library-defined lowering of pointer types. So you could add that write barrier or read barrier as necessary. Just an idea. It might be possible to allow mostly moving collectors by extending these RTinfo with this additional information if it might be ambiguous or not. And we would like to have also improve the way pointers are detected on the stack. Right now it's scanned conservatively, and that might also produce a number of false pointers. So, thank you for this. You can find this implementation, at least the heap part is in the runtime under this address on GitHub. The patches for the compiler, I don't think they are online yet. And yeah, thanks for listening. Questions?
Well, the first and most obvious thing is, what are the prospects for this? Oh, okay, yeah. Thanks. So the obvious question is, what are the prospects for this getting mainlined in the near future?
Well, we have to solve the issue regarding implementation of the RD. Well, the heap part, I think, is pretty safe and might be converted to a pull request pretty easily. Regarding the global data info, we have to figure out if there's a way to make the same logic work in under different platforms, on the other platforms. I think it should not be that bad, but the question is also, do we want to have this specific implementation in the compiler, or are we looking for some way to make it also a template, just like the RTinfo template? So these are some kind of blocking stones or decisions you have to make.
And one other question was, did you benchmark by any chance for Visual D using C's malloc and free for comparison?
Actually, I did not know. One reason is that I don't have the code to actually free everything perfectly. And also the DMC runtime gets pretty slow when it comes to a lot of memory. So it's probably not so good comparison anyway. So we would have to do it with another C runtime, I think.
Okay.
Yeah, you mentioned that the zero fill on structs produces false pointers. That was a bit of a surprise to me, but you're right. So I'm thinking instead of a zero fill, if we filled the pad bytes with all ones, we may be able to significantly reduce false pointers from the padding.
Yeah. As long as the highest word is set, it's
but the
usually
pad always
low.
tends to be the highest word, so
Yeah,
that's what works.
Yeah.
Right, you couldn't use BSS, but if you're like allocating things on the stack and things like that. So, anyhow, just a thought.
Question here. You said that you have ambiguity to know if something is a pointer or not. So, if I understand correctly, so far you're only marking which must be scanned and which is safe not to scan, but not exactly what's a pointer and what's not.
Yeah.
Okay.
So you see it here, for example, if its type is void, it's always marked as a pointer. Or if it's a union, it goes through composite template. And here the offsets are always, for example, 0 for all the members. And then you have the binary OR of all those bitmaps, and you cannot really tell, does a user mean a value or a pointer?
Sorry, and do you plan to add this information, or it's just an idea? Because
it's an idea. I'm not sure if it pays off really that much, because it also, the pointer bitmap now on the 32-bit, it adds about 3% memory overhead, and that would double, and some you have to make some guesses.
I was just wondering if you measured the difference in code size with all these templates being generated and just how
Well,
much.
actually, well, the info is pretty small that it's generated, the bitmaps. But actually, the code for RTinfo is actually compiled into the object files, because everything that is executed at compile time is also put into there, but it's all stripped in the link phase because it's com.dots, and so it's never referenced by the program. It's only used at compile time. So it's not an issue for the executable image.
So two questions. One is, you said that obviously if you're using a bitmap, you need more space for larger allocations than if you just do a pointer to an info thing. I imagine that if you have like a 10 megabyte array of structs containing interactions, you could actually use just one bit set for like one instance and then repeat it, right?
Yes.
Do you do this optimization? Or
no, not yet. No.
And the other thing is, could you expand a bit on the in-place race problem? Because I imagine if you like in place the type info or the like pointer info first, then you wouldn't get any problems, right? I mean, before you in place the data.
It depends on what's before and what's after. So say you have a reference in that memory area before you change the type info, then if you write it and then a collection starts, it might be it might be collected, and then it depends on what you write over it.
All right. I'd like to get a show of hands after this talk. Let's say for whatever reason we get a 5% performance hit by introducing precise garbage collection to D. And my question is, strategically, do you think this would be the right move? Raise your hand if so. On your average run-of-the-mill program, there will be a 5% performance hit by introducing precise collection.
32 or 64 bits?
64. All right, so you do care for 5%. All right, do you know what the difference between C and assembler was when people introduced C? 30%. 30%, my friends. Okay. My opinion is we should move forward with precise garbage collection. So why do you not? Why do you not? Why? You didn't raise your hand.
As long as it's optional.
As long as it's optional.
So where would this performance hit come from right now? Do we have any evidence that it actually exists?
Also, it's currently a bit more work to copy just a bitmap. That is mostly what the allocation gets a little slower.
Yeah, but okay, I guess I should wait for the mic. I was going to say, in practice, once you have all the extra memory laying around from false pointers and the effect that has on slowing down the GC, I think that any overhead is going to disappear. Yeah. So, and I mean, there's not going to be any overhead in code that doesn't allocate because we're not doing anything crazy with the stack to support precise stack scanning or anything like that. So I think that even if it shows up as a 5% hit in micro benchmarks, in reality, once you take into account for the overhead of having more memory consumed because of false pointers, it's not going to have that effect.
How much time do you save in your marks, in your scans and whatnot?
I don't see any real change because false pointers are actually quite seldom. So the usual test, is it in some pool or not, gets most of the pointer, or let's say because most of the values, because they're small, all those possible non-pointers. And so
I'm thinking is, once you start having false pointers, you have these blocks of memory that you suddenly start having to scan because you think there's a pointer to them when there isn't. So if you reduce the false pointer count, you end up with blocks of memory you just flat don't have to scan.
Yeah, sure. That helps. That's also what David wanted to say. But in this example here, the change wasn't that large that the execution was notably faster. But in this case, for example, if you take this as an example, that's here execution is almost solved for the
Last
main
question.
program.
Thank you.
It's not really a question. I want to react about your poll recently. So I did some tests like 1 year ago or something about false pointer and how much they do appear on 32 and 64 bits. And this is why I was asking 32 or 64-bit, because what I measured is basically the problem is non-existent on 64-bit system. They happen sometime, but they are like super, super, super rare. Even though on 32-bit it's a pretty serious problem, as I was quite surprised when I did my test. It's much worse than I would expect it. But I don't think it is worse to have a performance penalty on 64-bit system. There is way too few false pointer.
At the moment, you can version it out, more or less.
All right, so let's thank the speaker again. Thanks, Rainer. And we take -4 minutes break. Okay, so 2 minutes, okay? Out and in. Thank you.